Welcome to Brain Vision.
So we have this ideal reheat Rankine cycle with water as the working fluid. Operates in a boiler, and the boiler pressure here is 15,000 kilopascals or 15 megapascals. The reheater is at 2,000 kilopascals, so that's 0.4 here. And then the let's see here, the condenser's at 100 kilopascals, so 4, 1, and 6 are at 100 kilopascals. We're told that the temperature at the entrance of the high pressure and low pressure turbines is 450 degrees C. So we have the same temperature here and here, so 450 degrees C. Mass flow rate is, let's see here, 1.74 kilograms per second. And we want to determine the power used by the pump, the power produced by the cycle, the rate of heat transfer in the reheater, and the thermal efficiency. Okay, so we got a lot of work to go through here. So we can start by just kind of looking at the pump section, which is kind of the easiest thing to look at. Look at the pump. And so we know, again, we have saturated liquid here. So we have the enthalpy and the specific volume. The pump we're assuming is 100% efficient. So we can figure out from the pressure difference and the specific volume what the specific work into the pump is. From that, we can, an energy balance on the pump, we can figure out what the enthalpy at 0.2 is. That gives us then two properties at 0.2. And let's see here, we can then get at 0.3, we know pressure and temperature, so we can get enthalpy and entropy. At 4, we're assuming, again, an ideal turbine at this stage. So that would be I guess that would go into the low temp, no, that would be the high temperature or the high pressure turbine. So the high pressure turbine, we know then is ideal, and so is a low pressure turbine. So let's see here, we have then, so now we have S4 because it's equal to S3, and so now we have S4 and P4, so we can get H4, and that's 2,703 kilojoules per kilogram, with a quality factor of about 95%. We could obviously get T4 too, but we didn't need that, so we could see where we are as far as temperature goes here. Let's see here. So now we know H4, and we know at 5, we know temperature. We don't know pressure, but what else do we know at 5? We know that, what is it that we know at 5? We know, we know the temperature. And what else do we know at 5? We know the pressure, because, yeah, this is a constant pressure line. So that the pressure here is also P5. Forgot to write that. So we know the temperature and pressure there, so we can get the enthalpy at 5. We can also get the entropy at 5, which it looks like I didn't write down, but it's here because the enthalpy at 5 is the same as the enthalpy at 6. So maybe this was a 5. This is 5 and 6 because, again, we have an isentropic process there. Now we can go, we know that at 6 we have the entropy and we have the pressure, so we can find the saturation is about 98.8%. So again, this isn't really drawn correctly. We're out here closer. And then we can get the enthalpy at 6. So now we have the enthalpies everywhere, which allows us to then basically just use conservation of energy on every component and get what we need. So we know Qn is the enthalpy difference from here, well, from here to here, and then from here to here. So we have both. We have to add from 3 minus 2 and 5 minus 4 to get that enthalpy. And that winds up being, the specific enthalpy is 3,380 kilojoules per kilogram. And then the enthalpy out, we just need to take H6 minus H1, and we get this value. The net work is then just the difference in these two. So that winds up being about 1,150 kilojoules per kilogram. Now, we can multiply by the mass flow rate to get the actual power output, and that turns out to be almost exactly 2,000 kilowatts, or 2 megawatts. Now, to get the reheat power in, or the reheat temperature, the reheat heat flow in, we need to look at this section here. Right? So the specific heat flow in to the reheat section is H5 minus H4. Then multiplying it by the mass flow rate, we get about an energy into the reheat section, the reheat with the reheater of about 1,140 kilowatts. The pump, we know the specific work, multiplying it by the mass flow rate, we get the work going into the pump, or the power going into the pump is 24 or 27 kilowatts. Again, usually that should be much smaller than these as a check. And so then they want the efficiency. Well, we can just use the Q in and Q out, the specific Q in and Q out up here to get that. And that's just 1 minus Q out divided by Q in. Turns out to be 34%.